We will briefly introduce the concept of Earth as a system. I think I already mentioned in the introduction what we mean by system. Again, think of your own body as a system with its neural system, skeletal system, digestive system, cardiovascular system, and so on. Each one can do something by itself, but usually when they work together, they do something that's only done when they work together, right? Kind of approximately speaking. So Earth itself is a system. We can see many diagrams. We saw the Bretherton diagram, for example. Here we are looking at it as tropics to poles. We talked about the energy excess and the energy deficit. So energy deficit leads to things like ice sheets, which can grow really thick on land. Ice sheets or glaciers are basically snow falling and not melting in one year, more snow falling on top, getting compressed and converting into glacier, which actually flows under its own weight. Unlike frozen ice, which is brittle, glacier can flow like molasses, especially down the slopes of the continents and mountains and so on. Okay, then we have the greenhouse effect, carbon dioxide, methane, water vapor being one of the dominant greenhouse gases. We have the energy coming in and energy going out as back radiation, creating evaporation, precipitation, river runoff, sea level. There are volcanic eruptions which also change radiative forcing. The energy is moved by creating winds, and then water vapor is also moved as clouds and precipitated along the way. And then there is carbon as part of the system, as we already mentioned, because there is photosynthesis and vegetation which can sequester carbon. Ocean can take up carbon just by exchange and sinking, versus also photosynthesis. So it has what is called a biological pump, which can move carbon down, or a solubility pump, which is a circulation temperature pressure, which can move carbon as well. And we have plate motions, continental spreading, ocean plates forming, and deep water, surface water exchanges between them with upwelling, and so on and so forth. What matters most is what we already mentioned as feedbacks. So we have forcings. Whenever we say forcing, we always mean something that changes the radiative balance at the top of the atmosphere. So you have some solar energy coming in, some outgoing long wave that's trying to balance the system, but greenhouse gas increase, for example, traps more energy, so you're going to change the radiative balance. Same thing can be done by changes in Earth's orbit, obliquity, precession, and ellipticity, as we will see later on. Plate tectonics, mountain building, movement of continents can do that, of course, and has happened over Earth's evolution. Solar activity itself changes, sunspots, and the luminosity of the sun itself is increasing, and sun will eventually burn out in a few billion years. But when the solar system formed, sun was 30% less bright, less energy coming in. So there is the young sun paradox about how Earth would have had water in liquid form to support life, and so on and so forth. More close to home, climate system, we think of it as atmosphere, vegetation, land, surface, ocean, and ice, and there are feedbacks between them. We will see more and more of those as we go along. And then we produce climate variations with changes in atmosphere, warming, cooling, shifts in ITCZ, shifts in rainfall patterns, shifts in deserts. We have changes in ice, warming, and cooling, so glacial, deglacial cycles on long time scales, and now under global warming, glaciers on Greenland and Antarctica and the mountains melting, changes in vegetation because of changes in rainfall over, let's say, decadal time scale, because of deforestation, for also vegetation changes, urbanization. Changes in the ocean, increased carbon dioxide, for example, is creating ocean acidification, and also warming of the ocean is creating stratification changes, biology changes, and so on. And you have changes in the land surface either naturally or because of human activities. Okay, so these feedbacks are very essential. The revolution in satellite technology and in situ measurements and so on now give us not only lots of data on all spheres like atmosphere, cryosphere, aerosols, which are basically particles airborne, can scatter light, can absorb light, energy, can change cloud properties, can change albedo, and heat absorption by the atmosphere, and so on. Ships, Argo floats, and changes in sea ice measured with satellites and so on. And the other thing we should mention is there are now products called Reanalysis, which are basically models which ingest these observations through techniques called data assimilation. So if you, for example, go back 10, 20, 30, 100 years, there is not as much data, but the models can use radiation, for example, at the top of the atmosphere and produce climate. And they have their own reality because of either model errors or uncertainties in the forcing and so on. But dynamically, we can blend the data and the models to produce what are called reanalysis. So they are used for a lot of studies to understand processes that cannot be understood just by data or sometimes just from models. So reanalysis for the ocean, for the atmosphere, for the coupled system are all now available in multiple products. From multiple centers and institutions in several countries, from China to India to US, Europe, and so on. So what is model then? I said models can combine data and produce dynamically interpolated variables, essential climate variables. We have equations of motion like Newton's laws of motion converted into force and response, F equals ma types equations. In the 50s and 60s already there were models being developed, and Suki Manabe, we mentioned, was already doing climate sensitivity type experiments and already worrying about increasing carbon dioxide. Then the ocean models came along. By mid-90s we had also land surface models and ocean and sea ice models. Into the 90s they were all being coupled, and also we were adding atmospheric chemistry, sulfur cycle, land carbon, ocean carbon, atmospheric chemistry, like ozone formation and various other things. Late 1990s, when the IPCC assessments began to be carried out, we were adding more details of feedbacks between these various components, including dynamic vegetation. So vegetation was beginning to change in response to climate, and it was now it is beginning to feed back to the climate. Okay. So present-day models, what we call Earth system models, generally include carbon cycle, and as we saw in the first chapter, they don't include enough of human agency. That's the complaint of the social scientists, which is a legitimate complaint. And into the future, we're going to have more improvements in the processes with all the observations we have, better predictions, better projections, and so on. Okay, let me stop that there and then come back to the next podcast on where we go with those models and how we develop scenarios for the future, and how exactly do we make future climate projections, what goes into those projections.